Open up the newest interface for GPT 5.6 or DeepSeek v4, and you will immediately spot a new dial. It is a reasoning effort dropdown, letting you set the model from light all the way up to ultra. Click a higher setting, and before the model gives you its answer, a think block opens up. It dumps hundreds or thousands of words of intermediate logical steps, backtracking, self-correcting, before snapping shut and spitting out a brief final response. Watching that wall of text scroll by, it is easy to assume the machine is pausing to genuinely ponder your question. But these systems are not suddenly experiencing biological cognition. Those literal think tags you see are purely cosmetic. They are formatting wrappers injected so the user interface can neatly separate the scratchpad math from the final output and hide it from the user. What you are actually watching is the mechanical execution of inference-time compute scaling. Firmly pushing the reasoning effort to ultra is not an automated way to type think step by step into the prompt box. It triggers a distinct structurally engineered operational mode baked directly into the model's architecture. These specific trace blocks are forged through post-training through two specific methodologies: supervised fine-tuning, or SFT, and reinforcement learning with verifiable rewards, known as RLVR. Understanding how these back-end controls actually manipulate the generation of hidden tokens is the only way to effectively navigate the modern cost versus accuracy trade-off in AI deployment. To see why that trade-off exists, we have to look at the economics of model performance. There are two entirely distinct axes we use to make an AI more capable. This chart maps agent performance against API cost. The first axis is training scaling. This relies on the brute force method of increasing parameter count and pre-training dataset size. On the graph, you see it as jumping from a smaller model curve like Luna to Terra to Sol. The second axis is inference scaling. Here, the underlying model weights stay exactly the same. We simply allow the model to spend more compute by generating more tokens to solve a given problem. You are sliding up a single curve. Notice where these curves intersect. A much smaller model, pushed to maximum inference effort, can perfectly match the performance of a massive model restricted to low effort. For developers, this proves that latency can be directly traded for intelligence on the fly. But a standard, conventionally trained LLM cannot slide up this inference curve effectively because it has been trained to output direct, immediate answers. Scaling dynamic inference requires forcing the model to generate intermediate steps, which necessitates a shift away from traditional preference-based training. That brings us to reinforcement learning with verifiable rewards, the mechanism that induces these reasoning traces. When building their proof-of-concept R10 model, researchers at DeepSeek attempted an extreme approach. They skipped human-annotated supervised fine-tuning entirely and used pure reinforcement learning. The model generates a response to a complex math or coding problem. The intermediate words are completely ignored by the grading system. Instead, an automated compiler or math checker looks exclusively at the final answer and receives a rigid 0 or 1. The researchers guided the output structure by adding a symbol format reward, triggered only if the model encapsulated its intermediate scratchpad text inside literal think tags. Left alone with this binary setup, the model spontaneously starts generating long strings of intermediate tokens, simply because doing so maximizes its probability of getting the final answer right. During training, researchers watched the text stream as the model derived a complex equation, suddenly output the phrase, "Wait, I made a mistake," abandoned its current logic path, and generated a corrected approach. This self-correction behavior emerged natively from the reward function's objective math, bypassing the need for explicit human programming. Pure RL proves that reasoning traces evolve natively. The problem is that it creates an unwieldy, perpetually verbose model that spits out 1,000 words of thought even for a simple greeting, with no way to turn it off. To make these models viable for everyday use, engineers had to figure out how to take an always-on reasoning model and give it an off switch. They achieved this through an explicit supervised fine-tuning stage called thinking mode fusion. In Stream A, the training data pairs a /think system flag with a massive reasoning trace and a correct answer. Parallel to that, Stream B feeds the model a /nothink flag paired with an immediately closed think block, jumping straight to a short, direct answer. This dual-stream conditioning forces the network to associate specific system prompts with generating a full trace and others with generating an empty one. Once deployed, that training structure enables a highly specific execution trick. When a user or an API sets the reasoning toggle to off, the system sets a variable called enable thinking to false. This commands the tokenizer to literally pre-fill the context window with an empty, closed think block before the model even generates its first word. Seeing that its trace is already closed, the model obeys its stream B conditioning, bypasses trace generation entirely, and spits out the direct answer. The toggle forces a pre-filled string into the context window, triggering the model's SFT conditioning to bypass the trace and save compute. A binary on-off switch is simple, but modern flagship models like GPT 5.6 expose a continuous dial, letting you set the effort anywhere from light to ultra. Building a sliding scale requires moving the yawn formatting tricks and implementing effort-conditioned RLVR. During training, the system attaches a continuous floating variable, let's call it E for effort, to the prompt. That effort variable is then plugged directly into the training reward equation. The model's total reward equals its task reward minus a lambda penalty multiplier multiplied by the number of tokens generated. When the effort variable is set to low, that lambda penalty scales up. Every single word the model generates starts eating into its final score. To preserve its reward, it is mathematically forced to keep its token count as small as possible. Set the effort to high, and the penalty multiplier drops toward 0. Now the model has the budget to generate thousands of tokens to test out multiple logical paths without being financially penalized by the grading system. Implementing this in the real world carries a strict operational risk. If an API call enforces a hard compute budget that cuts the model off mid-trace, the network will often freeze or fail to return a final answer at all. To prevent catastrophic failures, architectures like Nemotron 3 Ultra inject random budget truncation into their training pipelines. Researchers take SFT traces, chop them off at random limits, and append the final answer. The model learns that if suddenly interrupted by the system, it must immediately synthesize whatever partial logic it has and output a definitive answer. When you turn the reasoning dial in an app, you are manipulating token generation penalty weights. The UI is dynamically adjusting the exact economic constraints applied to the model's logic generation. Mode fusion, continuous penalty RLVR, and budget truncation represent the core mechanical components of the modern reasoning architecture. Reasoning effort is simply the explicit operationalization and monetization of inference-time scaling. By exposing these controls, the entire strategy behind deploying artificial intelligence at scale has shifted. Enterprise optimization is no longer a static choice of renting the largest parameter model you can afford for a given task. In complex agentic deployments, that static choice is being replaced by autonomous task routers. These routing systems will evaluate an incoming query and dynamically adjust the lambda penalty and token limits on the fly. They will calculate the precise trade-off between tool latency, the cost of a failed execution, and the raw complexity of the prompt before the model generates a single word. We have moved from treating inference scaling as an unpredictable phenomenon to managing it as a controllable dial, allowing us to traverse the exact Pareto frontier of compute efficiency on a per-query basis.